In this next video, we want to look at the ideal gas law. The ideal gas law puts together all four variables, pressure, volume, number of moles, and temperature, into one equation. This one law, the ideal gas law, actually can be used to derive all the other laws. Boyle's law, Charles's law, Amonton's law, Avogadro's combined gas law can all be derived out of this one law. So if you know the ideal gas law, you actually know all of the gas laws. Based on the ideas of kinetic molecular theory, which we'll go into a lot more detail in a later video, it was important to be able to know the number of moles of gas that are present in a typical gas, and we can get a relationship. That relationship is the ideal gas law, PV equals nRT. This is a very fundamental equation for the gas laws in chemistry. Pressure is P, capital P. For the ideal gas law, it must be in either atmospheres or kilopascals. Volume, for V, is always going to be in liters for the ideal gas law. N is number of moles. R is an ideal gas constant. This is a number. This number will be based upon the units that you use for pressure. There will be two ideal gas constants. These will both be given on quizzes and tests and on the ACS exam at the end of the year. But for the ideal gas constant, it's going to be based on which one you use based on the units of pressure that you are using in the ideal gas law. And T is temperature in Kelvin. Now this ideal gas constant can be one of two things. We can do R, it's 0.08206. That is if we're in the units of liters, atmospheres per mole Kelvin. So if we're in the units of atmospheres, volume in liters, N in moles, T in Kelvin, we would use this for the ideal gas constant. We use 8.314, that's a decimal place, when we're in liters, kilopascals per mole Kelvin. So depending on whether you're in kilopascals or atmospheres, that's why we say we have two possibilities for pressure, atmospheres or kilopascals. We're always going to use liters for volume, moles for N, number of moles, and Kelvin for temperature. Depending on which pressure unit you use, you will plug in one of these two constants in for R. These over here on the right are the units for each of these. They are not a formula that you're plugging into. They are the units. Now, as I said, we can derive all the gas laws out of the ideal gas law. So let's look at a couple examples of this. We have PV equals nRT. So let's say we have Boyle's law. We said N and T were constant, which means if we take the ideal gas law, P times V, N is a constant, R is a constant, T is a constant, so we can say all of those are a constant, PV equals K for Boyle's law. Charles's law. We said in Charles's law, pressure and number of moles were constants. So if we take this and get volume and temperature on one side, we have nR over P on the other side, and we solve the equation to get volume and temperature on the same side of the equation. We know all three of these are constant, so we can say V over T equals K. You do the same thing for Avogadro. In this case, in Avogadro, we said P and T were constant. So if P and T are constant, we get the other variables, the constant variables on one side, the changing variables on the other. We get RT over P, all of which are constants, so we can say V over N is equal to K. We do Amonton's. In Amonton's law, V and N were our constants. So if we get P over T equals nR over V, N over V are all constant, so P over T equals K. And we can even do the combined gas law. The only thing that's constant is N. So we do PV over T, leaving the two things that are constant on the other side. So we get PV over T equals K. And you can see you can even do relationships between, say, V, or we've got between V and P and R and T. So let's say one of the relationships we haven't used, the relationship between pressure and number of moles. You could do P over N equals a constant by doing nRT over V on the other side of the equation. So you can come up with all kinds of relationships. Let's look at some example problems with the ideal gas law. What is the mass of 280 milliliters of carbon dioxide at 860 millimeters of mercury and 12 degrees Celsius? Now we know PV equals nRT. You know pressure has to be in atmospheres or kilopascals. So I'm going to convert this to one of those two. I'm going to choose atmospheres. So 860 divided by 760. I get 1.13. Volume needs to be in liters. So the volume is 0.280 liters. The temperature needs to be in Kelvin, so 273 plus 12, so 285 Kelvin. And now I can solve. So the pressure, 1.13, the volume, 0.280, equals N. The R I'm going to use is the one for atmospheres, 0.08206, since pressure is in atmospheres, and 285 for the temperature. So 1.13 times 0.280 divided by 0.08206 divided by 285. And I get an N in this case of 0.013 moles. It's asking for mass. So this is carbon dioxide. So I just need to convert this to grams now. 1 mole CO2. Carbon dioxide, oxygen 16, 2 of them 32, plus about 12.01 for carbon. So I get 44.01 grams CO2 for every 1 mole. It comes out to, in this case, 0.57 grams. Okay, another example problem. What is the volume of 22.01 grams of carbon dioxide, 115 kPa, and 30 degrees Celsius? So 22.01 grams carbon dioxide. I need to convert this to moles first. 1 mole, 44.01 grams. I get 0.500 moles. So that's my N. My P, 115 kilopascals. My T, 30 plus 273, so 303 Kelvin. So now I can plug in PV equals nRT. I'm going to do the algebra first this time, so I'm solving for volume. So volume is nRT over P. So the volume, 0.500. I'm using pressure in this case in kilopascals, so I'll use 8.314 for my R. T is 303, and my pressure is 115. So 0.5 times 8.314 times 303 divided by 115 gives me a volume of 10.9 liters. Okay, so that takes me through some examples of the ideal gas law. It's PV equals nRT, pressure always in atmospheres or kilopascal, volume in liters, N is number of moles, and T is temperature in Kelvin. R is the ideal gas constant, 0.08206 liters atmospheres per mole Kelvin, the one you'll use if you're in atmospheres for pressure. and 8.314 liters kilopascals per mole Kelvin.